Yeah, all right. Yes. So the announcement is here it goes that to the next week, right? That is on 17th and on 24th, I will not be able to hold the sessions because I am traveling. Okay. Uh, I can take makeup sessions for that, but since this course is a repetition, and last year also I took the same course, so the recordings are actually present at my on my website on my YouTube channel, so you can refer them. So I will not be holding sessions on 17th of February and 24th of February because I'll not be here. I will be traveling. So for that, I will be posting the relevant materials on my YouTube channel. Don't worry about it. You will get the recordings, but they will be of the last year's sessions. Okay. You should be able to. I mean, I have solved some examples there also. You should not have a problem in understanding them. All right. Okay. So okay. So let me start now. The week session. Second. Yes. I hope my screen is visible, right? Okay. So today, in this session, we will be looking at week 3. But before anything like that, as always, let me start with the introductions. So the course is Analog IC Design. All right. So this is an NPTEL course, and the instructor for this course is doc. They are two. So this is the instructors are Dr. Shankar Aniruddhan and Dr. Nagendra Krishnapura. Both are professors in the electrical engineering at IIT Madras. All right. Myself, I am the tutor for this course, and my name is Mayank Anupam. I am a PhD student in the Department of Electrical Engineering at IIT Kanpur. All right. So today we will be discussing the contents that were covered in the week 3 of the course. All right. The summary for the content is here. It is written here that we looked at negative feedback with parasitic poles and zeros. Right. We looked at them. We also learned about so we saw that the effect of parasitic poles and zeros is actually very similar to what we saw for ideal delay. Right. So some poles and zeros, they somehow introduce some delay in the system, and then we looked at some examples how with these poles how the system behaves, how the system's stability is affected, and then we solved some a few examples with two poles, three pole system, right? And we saw what should be the location of those poles, right, to make sure that the system behaves properly. And but after that we saw that this becomes very difficult to actually characterize, right? If the system has a lot of poles at different locations, you cannot always keep for hand calculation or for any kind of analysis, you cannot always go back and apply unit step and see whether it is converging or not, right? So we need a somewhat easier method to make to analyze our system. So for that we looked at Nyquist criterion, right? We looked at Nyquist criterion, which actually is a very simplified, which actually presents a very simplified picture to evaluate whether the system is stable or not, right? We only have to plot the loop gain of the system, and then that loop gain has to be plotted on the on the S plane, and then we just have to see whether the loop gain plot actually encircles the -1 comma 0 point clockwise or not, right? If it doesn't encircle it clockwise, then we are safe, isn't it? That's what it is. So, and yeah, so that is how we saw this. Then today I will actually be giving you. This is not actually in this week. So this is something which I added here in the content. I will try to motivate you as to why in a system, in a negative feedback system, if there is a if there is a 180-degree phase lag and the loop gain is greater than 1, system becomes unstable. So this I will try to motivate you why that should happen. I'll try to provide an intuition. However, having said that, this particular analysis which I will do, particular intuition, it's only this kind of intuition is only valid for purely for systems which have only poles. Okay, if the system has zeros, then it is not strictly true. Anyway, so we'll come to it later when we'll see this. Then we will look briefly at what is phase margin, and we'll talk a little bit about body plots, right? Yeah, so this is basically what we covered in week 3, and today what I'll be covering. So before that, let me ask you this. In week 2 assignment, do you have any doubts? In week 2 assignment, do you have any doubts? All right. All right. Thank you. Uh, okay. At this point, I also would like to ask you any feedback about the sessions. Do you have any feedback about the sessions? Any changes which you would like me to make, or anything which you have in mind?
No, sir, this is okay, sir.
Thank you. Thank you very much. All right. So if there's nothing wrong with the flow, so let me just go ahead with the session. All right. So, Ayan, you have doubt in the second lecture of this week. So exactly, can you tell me what is the doubt, Ayan?
Hello, hello, sir.
Yes. Yes.
The where sir was evaluating that one plus gh, and
Mm-hmm.
he put that omega is equal to j omega. Okay, then he put that complex term to zero and real term to zero. Okay,
Mm-hmm.
so by doing that, we can know that there will be, I mean, the crossing of j omega axis. Okay,
Uh-huh. Yes.
so after that, sir mentioned that what's the condition that the pole will lie on j omega axis, that
Yes.
p omega equal to p2 and p2
Hmm.
equal to omega u loop by 2.
Uh-huh.
Then sir write that the system will be unstable if
Mm-hmm.
p2 less than omega u loop by 2. And
Hmm.
then again after two slide later,
Yeah,
sir
there was an
mentioned that.
issue. That was a typo. It should have been P2 should be greater than omega u loop by P2. Okay. It should be, SR had written like this, right? It should be like this. It should be greater than. That should be the condition for stability. Got it?
So by when we go for root locus method, so
Uh-huh.
here only three pole is there. So we can say that one pole is going from one pole is going real axis
Mm-hmm.
to negative real axis. Okay,
Mm-hmm.
and two pole is going like from the, what do I say, point of convergence to one plus 60 degree and one will be minus 60 maybe. Yes, actually say, I mean मैं हिंदी में बोलता हूँ, ठीक है.
All right. Go
ओके,
ahead.
मैं जो जे ओमेगा एक्सिस के ऊपर दो पोल होना चाहिए, राइट.
Okay.
हाँ, तो इसमें अगर रूट लोकस के हिसाब से जाऊं तो के हिसाब से मैं देख सकता हूँ कि के अगर बढ़ेगा तो वो राइट साइड पे शिफ्ट होता होता जाएगा. इधर तो P2 है, ये शायद मैं कोई मैटलैब पे डाल के देख सकता हूँ, लेकिन ये एनालिसिस करने के बाद कैसे पता चलेगा कि ये ग्रेटर देन होगा या लेस देन होगा, मतलब विजुअलाइज
Okay.
कैसे करूँ.
Okay. Okay. I'll try to motivate you on that today. Okay. All right.
ओके.
But anyway, this should be greater than, okay, for stability. So this, I think, was a typo in the lectures. I will try to motivate. I'll try to address your question. Okay, today. All right. Fine. Yeah. So let me quickly start. So first, let me address this point. The first point. Um did you guys understand why do we talk about this parasitic poles and zeros, by the way?
हाँ,
Because they can
क्योंकि
cause delays and
Yeah. So how exactly do you think poles and zeros cause delay? in the system?
Five.
They are introduced by this the capacitors, the parasitic capacitors, and
Yeah, yeah.
charging and discharging them takes time. So, I mean, there would be an inherent delay because of that.
Yes, good. You're right. So, anyway, so exactly, you are correct. Fine. So
Sir,
we know that yes,
when we perform a layout, then the line causes a coupling capacitor and the RC delay model. Then the delay comes into picture.
correct. That is all. They are all correct. Uh, exactly, you are right. Now, the thing is, uh, in the second week, we learned that if we put any basically the all the analysis was done with ideal delay, right? There was an ideal delay in the loop, right? If you remember, there was this Vi, and this was the situation. There was minus, so there is Td, and here let's say this is K, pardon, and there was an integrator here, right? Then this is what we had. Yeah, if you remember, this is what we had, right? And we did our analysis with ideal delay, correct? And then we saw that ideal delay actually is not a good thing because delay in a feedback loop creates problem. Hello? Yeah, I'm sorry, the internet connection was not all right. I am audible, right?
Yes,
Okay, fine. So we saw that delay in the system is not at all good news because in a negative feedback loop, delay can cause a lot of problems. System can actually become unstable, correct? So delay, this is not a good news. Now, as it turns out, in practical system, you will not get this ideal delay. All right, this is not this ideal delay kind of a thing will not have anywhere. You will never get an ideal delay in system. The delay manifests itself in terms of as a result of parasitic capacitances or any capacitors or inductors that are present in the circuit. All right, am I am I coming through? Are you able to understand me? All right,
yes.
so in practical systems, let me just make this point again. In practical systems, a delay results. Okay, that is understood, right? Now, if you all remember, what is the transfer function of this guy? A simple RC circuit. What will it be?
1 upon R SRC plus 1.
Right? So, what is the pole?
1 upon RC. Minus 1 upon RC.
Right. The pole location is minus 1 upon RC, right? Now, we know that this system has one pole, right? And what is the unit response? If someone asks you what is the unit response, if this is a unit step, sorry, unit step response, I wanted to ask. So, what is the unit step response here? How will it look at this point at the output? Hmm? How will it look at the output?
Uh,
Slowly
it will
charging.
be an
First,
exponential,
Yes, exactly.
decaying
So,
exponential increase.
in response to the input, which goes like this, the output will be slowly rising, right? It will slowly rise. Okay. So clearly, it looks like the system is delayed, right? I mean, this is what it means when we say that the system, that there is a delay in the system. It clearly looks that whatever due to the systems, due to the input, the output actually looks like the input after some delay, right? It looks like it, isn't it? I mean, this can be, you can say approximately this is the delay, right? Approximately this is the delay, isn't it?
Yes. Right.
So, in any practical system, the delay is not, you will not get an ideal delay. It's rarely, I mean, no, there's nothing ideal in this, in the practical world. You will not get an ideal delay. But the delay that you will be seeing practically in whatever design you take, the delay will come because of the constant, the finite time that it takes for the capacitor or the inductors to charge or discharge. Got it? So having, I mean, this is not just for the capacitor, even for the inductor, you will have that same situation. That is, let's say you have an inductor here, which is uh, sorry. Even for this, you will see that the the current that will flow in the inductor will actually be will actually have this kind of a profile. Okay, got it? If you
Yes.
give a unit, sorry, if you give it a unit step here, the current that will flow through the inductor will have this kind of a profile. Okay, this kind of a profile. Fine. Now this is clear. This is not a problem. Now tell me something. How does a zero affect the system? So we know that I mean, from this analysis we see that poles are always a problem in negative feedback, isn't it? They are always a problem. They will always cause some delay, isn't it? This is understood. All right. But what can you say about zeros? First of all, tell me something about poles. Is the right half plane poles good thing or bad thing?
Bad thing.
Bad thing, right?
That thing.
Yeah, right half plane poles we should not have. Definitely, we should not have right half plane poles. Having said that, there can be systems where in the in the loop gain expression you can have. So basically, what I'm trying to say is that uh, right half plane poles are not good only for the overall system. Let me just make this point here. Uh, so RHP poles implies what? The system is unstable, right?
For closed loop system.
Come again?
For closed loop system, if RHP pole.
Yes, exactly. Yes, exactly. Unstable. So this is for closed loop. So RHP poles I'm talking about, this is for closed loop system, the overall closed loop system. Okay. So if we have RHP closed loop poles, then the system is unstable. But so what do we want? We want LHP closed loop poles, right? We want LHP closed loop poles, which means that then it will guarantee that the system is stable, right? It will guarantee that. But uh, so what I'm trying to say is that in this particular, whatever we will be learning today or in this course, we'll only be seeing cases where the even the open loop system, okay, or basically loop gain, open loop gain also has uh, LHP poles only. So there can be cases where the where the loop gain expression has poles in the right half plane, but the overall system will be still be it will still be stable. Are you understanding what I'm trying to say here? So it can happen that this is your loop gain expression. Okay, let's say your loop gain expression is 1 by 1 plus s by p into dot 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 1 plus s over pn. P1 and p, let's say this is n, and that let's say that suppose Pn, or let it be a naught. Okay, let's say that Pn is equal to Pn is a RHP pole. Okay, however, if you find out the closed loop gain, if you find out, it can happen, uh, but closed loop gain may be stable. So is the point clear now what I'm trying to say? It can happen that the open loop system has poles in the right half plane. I mean the open loop gain expression has poles in the right half plane. Got it? But even then the overall closed loop system can be stable. So that is what I'm trying to say. It can happen. However, we'll not be looking at those cases. We'll be looking at only those cases where all the poles of the loop gain expression are in the left half plane. Got it? Is that point clear?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay.
Yes.
Yes. Good.
Hello, sir.
Yes.
I have one doubt in lecture that has been uploaded on NPTEL.
Uh-huh.
In that, sir has told me that P2 is greater than omega u loop divided by 2. When P2 is greater than, when P2 is less than omega u loop
There was a
divided.
typo. There is a typo there. Okay, this question was just asked now. It should
Sir, if
it should be omega u loop P2 should be greater than omega u loop by 2. Sir has written P2 is less than omega u loop by 2.
yes, sir.
Yeah, there
And
is a
sir,
typo.
when there is no pole,
Mm-hmm.
the difference between when there is no pole and when there is pole, the difference between the delay between them is 1 upon P2. Is 1 by
Yes.
P2.
Yes. I mean, only when there is a single pole in the system.
Yes, sir. And if there is multiple pole, then it is 2 by P2 or n by P2.
I mean, that can be said when you are very, very, very. It
Let's
is not exactly true, but it is true for a very small range of frequencies. I mean, when your frequency is very low. Yeah, yeah, you can say something like that. For unit
let's
step, yes, you can say that.
multiple poles at one location, then it will be n upon P2.
Yeah, yeah, it will be for. Yeah, it is true. Yes, you can say
So,
something like that.
if P2 is greater than omega u loop divided by 2, if we take higher value of P2, then this delay will uh, getting less. So
Yeah. So
there will be contradiction, like
no.
if if we take
If the
P2
P2 is becoming larger and larger, which means what? The
1
system
upon
is
P2 less, then
huh. Which means what? All right. So let
then
me ask you something.
then
If oh, one second. In this particular expression, tell me if P1 becomes larger and larger and larger. So what is the system going to behave like? Where is
Stable.
the system tending? So
uh,
what would this system look like if it had no
it
poles?
become more
If
stable, sir.
if it had no no, 1 second. This loop gain expression has a lot of poles, right? You can see here. It
Yes,
has
sir.
n number of poles. Now tell me without any pole, how will the loop gain expression look like? L of S.
It's A naught.
Simply
Only a naught, right?
Yes, sir.
It will look only like only a naught, right? Which means that a system has infinite bandwidth. The system is has infinite speed. Anyway, so this is what the system loop gain expression will look like if if the loop gain expression has no poles. Now tell me, if P1 and all the poles is becoming larger and larger, if P becomes larger and larger, where is the loop gain tending? Tell me.
Again towards stability, towards a naught.
Yeah, it is tending towards A naught only, right? The loop gain expression. So the easiest way to look at this is, if P1 or if all the P's they become equal to infinity, they tend to infinity, what will be the loop gain expression?
It will be a naught.
Not.
Exactly, right? So so what I'm saying is, if the system's pole location is actually moving away, which is if it is moving farther away, if the poles are moving farther away, which means the system is actually becoming more and more faster. It is becoming faster and faster, which means that the system is actually moving towards the case where the system had no delay. Got it? Even in
Yes.
the case where the example that Sir gave, that you have sorry, you have this kind of a thing, right? So if you only had a 1 over s kind of a thing, so this is an integrator, right? The expression is for an integrator. If you give a unit step to this like this, what will be the behavior of the system that is going to come out? What will be V out? If V in is a unit step, if V in is a unit step,
Ramp. Ramp.
it will be ramp, right? It will be ramp. Exactly, right? Now tell me, the system which had one more pole, something of this kind, 1 over s plus p, or sorry, 1 plus s over p. So what? So basically, it was something of this kind. It has now an
Del-
integrator, and there is also a delay, right? So what was the response of this system?
uh, right shift by 1 upon P.
Yeah, it looks something of this kind, right? Sorry, isn't it? So after a very long time, it looks like there is a delay of 1 over p2, right? Or 1 over p1,
Yes, sir.
right? Now if you keep increasing p1, what will happen? This will
Delay will reduce.
delay will reduce, right? It will keep coming closer and closer, right?
Yes,
So
sir.
which means what? The system is moving towards ideal condition, right? Is that point clear?
Yes, sir.
Yes. So basically,
Yes.
that is why uh, the system in general, if the poles are moving farther away, in general the system will move towards ideal cases, okay, ideal condition where the system does not have any delay, and thereby the system's stability should improve if the poles are becoming farther and farther away. Got it? In general, if the poles are moving farther away, which means that the system is actually moving towards stability.
So then P2 should be less than omega u by 2 for
No,
output
no, no,
for
no. It should be P2 should be greater than, right? Omega U
this
loop.
stability condition. No, sir?
Yeah, stability condition P2 should be greater than.
Okay, sir. Clear.
Yeah. Anyway, so this was slight digression. So this is what I wanted to say here, is that we will only be looking at cases where the even the open loop gain expression poles are actually in the left half plane. Got it? And then we'll be judging. Now, so this is understood, that if the system has if the loop gain expression has poles, and they will always be left half plane poles. If the loop has left half plane poles, then the so left half plane poles will look something of this kind, right? So this will always delay the system. Understood? There is no doubt there, right? Another way to look at it, that the system is actually delayed by the poles, is if we try to look at the phase of the expression. So bear with me for some time. Mm, we have single RC circuit here, and we already saw that the h of s for this is what? 1 over 1 plus src. right? So tell me what is the, so if I evaluate h of j omega, what will it look like? 1 divided by 1 plus j omega rc, right? This is what it will look like. So tell me what is the magnitude of h of j omega? What is the magnitude of h of j omega?
1 by
1 by
under root
square root
of
of 1 square plus omega square.
Yes, good. Now tell me also what is the phase of h of j omega?
minus tan inverse of
Minus tan
omega c.
inverse, right? Minus tan inverse of
Omega c.
Omega
Omega
RC.
RC.
omega rc, right? Isn't it? Now tell me this uh, term inside here, is this positive or negative?
Positive.
It is always
Positive.
positive, right?
Positive.
It is always greater than 0, correct? So what will happen to this overall term?
That will always be negative.
It will always be negative, right? It will always be less than 0. So if a system has negative phase, if sorry, this is a response, right? So in this response we can see that in V in to V out, so V out will be what? H of j omega times V in, right? This is what we'll have, where V out is actually of at some omega, right? So this is what we have. Whatever sinusoid we apply at the input, whatever input we apply here in V in will be multiplied by this h of j omega, and it will come out as V out, right? So so tell me, if the system has this negative phase, if the response has this negative phase, what does that mean? Phase is, what does that mean? Input is getting multiplied by a system which has negative phase response. What does that mean?
Phase lag, delay.
Phase lag, exactly, yes, phase lag, correct. So whatever input you apply, it will be the output phase will be lagging the input, isn't it?
Yes, sir.
The output will be lagging the input in terms of the phase response, correct?
Yes, sir.
Right? So one way to see this is if you apply a sinusoid here at the input. So let's say this sinusoid looks something of this kind.
Why it is minus tan inverse, sir?
So that comes out from the expression, right?
Which expression?
Okay, 1 second. Yeah, so tan inverse actually, so what is the phase I asked here? What is the phase of this h of j omega? How do you calculate phase? This is h of j omega. I am asking what is the phase of h of j omega? How do you calculate phase of j omega? Well, phase of any complex number. How do you calculate the phase of any complex number?
Tan inverse of y by x.
Yes, it is tan inverse of y by x. What is y and what is x? So this is for if the complex number is x plus jy, right? Then it is tan inverse of y by x. Correct?
Yes.
Yes. But if the system is something of this kind, tell me, if your complex number is a by b, okay, both a and b are complex numbers, then what is the overall what is your overall phase of this system? Phase of this number? It will be
Okay. Phase of A minus phase of
phase
B.
of a minus phase of b, right? Is
Yes,
that
sir.
point clear?
Yes.
Yes,
Yes.
sir.
Yes. So if this is the condition, then tell me, so does this look something of this kind?
Yes, sir.
So what is the phase of 1? What is the
Zero.
phase of
0.
1? It is
Zero.
0, right? So angle of h of j omega is actually equal to angle of 1 right? Minus angle of 1 plus j omega RC. Is that point clear?
How angle
Yes.
of 1 is 0, sir?
Yeah, exactly. So angle of 1 is 0. So 0 minus this, right? So 0 minus tan inverse. This is what I've written.
No, how angle of 1 is 0?
Oh,
Because component of J is 0.
exactly. So what is the angle of
One.
any complex number? What do we say when we find out when we say that the angle of any complex number we want to find out? So this is a slight digression. Please bear with me. Let us help our friend here. So we have this. Let's say I have a complex number C, which is equal to some A plus JB. Okay. So what is meant by what is meant when I say that? Sorry, 1 second. 1 second, please. Yeah. So what is meant when I say I want to find out the angle of C? If you try to plot this complex number, so this is understood that this complex number is not does not have a single. A complex number has two different entities, right? A real
Real and
part
imaginary.
and imaginary part, right? It is always represented by two entities. Always, a complex number has two separate independent entities in it. Okay, so when I say a number is complex number is there is a complex number, it needs at least two information, right? So to plot it, you need at least two axes, isn't it? To plot any complex number, you need at least two axes, correct? So this is x, this is y, right? So let's now ask you, what is, if you say what is this complex number C, A plus JB? So what do you have to, how do you plot it? You first find out the x-axis here. X-axis is how much? A, right? So let's say this is A, and then you also find out what is y. So this is B. So this is your complex number, right? This is A plus JB. Is this point understood?
Yes, sir.
The person who was
Yes,
asking me how
yes,
to calculate.
yes, sir.
Yeah. So now, if I so what is the so if I ask you what is the angle, what is the phase of this particular complex number, what you have to do is you have to find out that if you draw a line, if you draw a vector in this direction to this point, what is the angle of this? Correct? What is the angle here? Isn't it?
Yes.
Yes. So tell me, what is the angle here? Tell me. What is the angle here? This length is B. This length is A. What is the angle? Theta.
Tan theta equals b by a.
Tan theta equals B by A. Is that point clear?
Yes, sir.
Yes. Tan theta is equal to B by A. So tell me what is theta? Theta is tan inverse of B by A, right?
Yes.
So now tell me if I have a complex number which is simply 1, or rather let's say a complex number does not have any imaginary part. Let's say I have C is equal to my new complex number, let's say C is equal to A, simply A plus J 0. So this basically its imaginary part is 0. So what will you say, where will it lie on this
0.
complex plane?
0.
No, on this complex
The
plane where?
x-axis. The x-axis.
Yes, right, it will lie on the
A.
x-axis, right? It will lie here,
A.
isn't it?
Yes, sir. Yes.
Yes. So the vector that we will have will be pointing in this direction. So what is the angle of this vector with respect to x-axis?
0.
It is 0, right, Jayakumar? Uh,
Yes,
Hello,
sir.
Jayakumar. Yeah, you had this doubt,
Yes, sir.
right? The
Yes,
angle is
sir.
0, right? Another way to
Yes.
look at it is if you're so in this case, what is the value of b? B is equal to 0, right?
Yes.
So what is the theta tan inverse of
0
b
by
by a,
A.
which is tan inverse of
0 by A.
tan inverse of 0 by a, and this is 0, right?
Yes.
So this is why angle of 1 is 0. Alright? Okay, fine. So now let's move ahead quickly. Alright, so this is V out so when we have this phase delay, how will this look like? This is a sinusoid, okay? So this is, let's say it starts at 0 here. This is your 0 point, let's say. So if there is a phase delay here, how will it look like? How will the output look like? Hmm?
So, I mean,
It
whatever
moves
we are
right
getting,
side.
that will be delayed.
It will be left shifted, right? Like something of this kind.
Yes, yes, yes.
So let me just copy and paste. I do not want to do the same drawing again. So copy, paste. Let's use a different color here. Then it will look something of this kind, correct? Isn't it?
Yes.
Yes.
So so this is your V out. So it is there is a phase delay, right? And that phase delay actually, yeah, there is a phase delay of,
It will only happen when the magnitude is 1 of h of j omega is 1,
yeah,
right?
correct. I mean, there will be a magnitude change. I'm not denying that. I'm just saying that I'm right now I'm focusing on the phase. Got it?
Okay, sir.
Huh. So there will be a phase change, and that phase is actually you can see that it is actually now delayed, right? You can see that it is actually delayed, isn't it? System is
Yes, sir.
actually delayed. The red curve was the input, the blue curve is the sky blue curve is the output. And you can say that you can clearly see that because of this phase delay, there is a equivalent delay in the system. Got it?
Yes, sir.
Yes, exactly. Thank you. So this is how we get delay in the system because of poles. This is now very clear. Now tell me what happens if we have a zero. How does zero affect? Does this add delay? Does this add what does this do? Zero
That
in the system.
depends on the location of 0. If it's in right side, maybe it will lag the system, and if it's in left
So
side, then it
okay. So is
will
that
add.
point clear to everyone? Is that point clear to everyone?
Can you please repeat it once?
Okay. So we want to understand what is the effect of zero in the system, right? So our good friend here said that the zero can actually delay system if the zero is present in the left half plane of the left half plane of the S plane. Sorry, my bad. I'm sorry. The zero can actually delay a system if it is present in the right half of the S plane. Okay, that is what our friend said. And it can advance a system if it is present in the left half plane. So this is what our friend said. Let us try to understand how does this do that. So for looking at that, first let us understand. We will again try to understand it first using the expression, okay? Because this is very easy to see. If the angle of h of j omega will be positive, which means that the system is somehow getting advanced, isn't it? If the angle is negative, which means that the system is getting delayed, correct?
Yes, sir.
Yes.
But if the angle is somehow positive, then what does this mean? It means that somehow the system is getting advanced, isn't it?
Yes, sir.
Yes.
Yes.
So
Yes.
what does the zero look like? So h of j omega, let's say h of j omega is h of s is 1 plus s by omega z, right? Let's say this is the situation. How will the systems, so again tell me what will be the h of j omega here? 1 plus j omega by omega z, right? Correct? So tell me
Yes.
Yes, sir.
Yes.
what is mod of h of j omega? 1
Root
plus
over
1 plus omega by omega z whole square under root.
Correct? Yes. And what will the angle look like? Angle of h of j omega, phase of h of j omega.
Tan
Tan
inverse
inverse
of
omega
omega
Tan
by
inverse
omega
of
z.
omega by omega z. So
Yes,
again, tell me whether this expression is positive or negative,
positive.
right? So overall, it will become greater than 0, right?
Yes, sir.
So this actually means that the system will become advanced, isn't it?
Yes, sir.
Now tell me what happens if I use 1 minus s of z omega, 1 minus s by omega z. What will happen to the magnitude? Will magnitude change?
Magnitude will remain same.
Yes. What will happen to the angle?
Angle will become minus.
Minus, right? Minus of, sorry, minus of tan inverse omega by omega z, right? So
Yes, sir.
in that case, what will happen to the system? It will become less than 0, right? The
Delayed.
h of j omega will become less than 0, which means what? The system will be
Delay.
delayed.
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 And this means what? System is
Leading.
Advanced.
Yes, lead.
advanced, right?
Advanced. Hmm.
All right. So this is very easy to see if you look at the I mean the maths of this. But tell me something. I would like to ask you. This is a slight digression here. Can is it? It looks like from this expression is that if we somehow get if we are somehow able to get this positive here, then somehow the system will actually become somehow the system will start predicting future, isn't it? It looks like from here, isn't it, that the system will start predicting
Yes.
future. So even
Yes.
whatever input you give, the output will actually be advanced version. It means that output is coming up, output is coming out even before the input was applied, something like that, isn't it?
Yes, sir.
Yes.
Yes, is that point understood? If this if the omega z, uh, if the 0 is in the left half plane, which means that the system is advanced, right? And if we have this h of s in this manner, okay, if we only have if we only have zeros in the system, and if all the zeros are in the left half plane, it looks like that the system is seeing in the future, isn't it? Correct?
Yes.
So is that possible?
कुछ तो गड़बड़ है.
Yeah, right. So
No. No.
what do you think is the issue? I mean, is that possible? That is not possible, right? That is not physically possible. This is definitely not possible. It only God can do that. Only God can look into the future. So tell me, so from your logic, what do you think should actually be happen in the system? One second. Yeah, I'm sorry. One second. My screen is actually. Let me share the screen again. Suddenly it went off. All right.
Such system don't exist.
Exactly, such systems will not exist. So what is it? How will the? But there will be systems where there will be zeros. Okay, there will be system where there will be zeros. So how will the system have zeros? Definitely, it is not possible to have systems which will have only zeros, right? It is not possible because if you have only zeros and if the system has only zeros, then basically what will happen? It can become advanced, right?
Yes.
So that is not possible. So what do you think should be a case which is practically feasible, which will which God can allow to appear in this universe?
I think we might have poles either
Exactly,
equals to number of zeros
exactly,
or more than
exactly,
zeros.
exactly. Very good. So as it turns out, uh, this whenever you get a zero, you do not get it always. You never get it alone. Okay, it will always appear with a pole.
Yes,
You will
sir.
never get a 0 which is standalone. You'll always get a pole with it. It always comes with a pole with it.
So in this case, we can see that a pole exists at infinity. Like,
No, 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 no. There will be a finite pole. If there is a finite 0, there will be a finite pole. Got it?
Yes.
Yeah. If there is a finite pole, there is a finite 0, there will be a finite pole. The other way to look at it is, even without looking into the delay, you can actually look here in the magnitude response. What happens to the magnitude as omega increases?
Increases.
It keeps increasing, isn't it? If the frequency is very high, it will keep becoming higher and higher, isn't it?
Yes, sir.
Something. So if the frequency becomes very high, let's say infinity, what will happen to this? It will become
It will
It
infinity.
also
will
be.
be infinite.
Yes, and
It
as
will be
it turns
infinite.
out, it means what? It means that there appears to be a system which has
finite.
infinite gain at very high frequency, which means that the system is acting very, the system can process infinitely fast with infinite gain. Is that point clear?
Yes.
That is not
Yes.
possible, right? That is clearly a that is clearly which that is that clearly defies that's things which we see in nature, right? So this is not possible. So whenever we have a 0, whether it is left half plane or right half plane doesn't matter, it will always come with a pole. All right, whatever 0 we have, it will always come with a finite. If we have a finite 0, it will always appear with a finite pole. Got it? So in general, for any practical system, if we have a transfer function h of s, then there will be a n of s and d of s, right? There will be numerator and denominator, right? So the degree of denominator, okay, if it is it will be a polynomial in s, right? So the degree of a denominator will always be greater than the degree of numerator, greater than or equal to. Okay.
Sir, in the case when it will be equal, is there a condition where the pole has to be greater than the zero to offset the difference? I mean,
What is that?
uh, sir, like imagine if there's one zero and one pole,
Huh?
right?
Okay.
The effect of pole has to be more than the zero to offset the advance. Like, uh, you understand, sir? If there will be a zero, it will cause say x amount of advancement. So the pole has to be greater than x to bring the net.
Oh, yeah, I mean, yeah, it will, there will be something. You can never have a zero delay in the system. So you can always play with math and create your own transfer function, but any practical transfer function, which we'll see in the system, will always have some delay, and yeah, whatever you are saying is correct. If there is a zero, and let's say if it is a left half plane zero, which means that the system is getting advanced, the pole will do its equivalent job and make sure that the overall system is delayed. The delay will be reduced, but still there will be a delay. Okay.
Yes, sir.
Yeah. All right. So now let us try to understand it in terms of. mm yeah, Ravi, you have a doubt?
Yeah. Yes.
Huh.
So, in systems where we want, like, let's say where we have a significant delay and we want to improve the performance, like making the
Huh.
delay less,
Yeah.
we can introduce a zero as well, right?
Exactly. Exactly. Very good point. This is what you will see is routinely done. Whenever you have a system which has a lot of delay, there is actually routine, it is routine practice to make sure that the delay is reduced either by reducing the increasing the pole, either by pushing the pole away much away, or by introducing another zero. It is actually routinely done. In fact, uh, there is a compensation also. There is a feedback in you will not learn in this course. I don't think you will. There is you will learn Miller compensation in the next lecture, or maybe next lecture only, next week only. I don't know, but there is a Miller compensation which actually makes sure that the poles are pushed away. But there is another compensation to make the feedback system stable, which ensures that there is a zero in the system, and that makes the system faster, right? So there is actually, this is actually routinely done, whatever you said. Any other
Sir,
doubt,
Thank you.
Ruby?
like the delay had a physical significance, like it being a capacitor.
Huh.
Uh, so, sir, how can we explain the
I'm
advancement?
coming to that. I'm coming to that. Yes. So zero, let us try to understand this now. So we all know there is a something called a low pass filter, right? We all know there is a low pass filter. We know
Yes. Yes.
something like that, right? There is a low pass filter in the which is very, which has a practical significance. There is a filters we know, right? And there is a low pass filter we know. So can you tell me
Yes.
what will the low pass filter look like? If this is a practical scenario, the low pass filter will not have a steep something like this. It will always have a gradual roll off. Okay, something like this. So how can you make a low pass filter? You can create a pole here, right?
Hmm.
Right. In fact, this is how it will look. So the RC circuit that we have here, it is a low pass filter, isn't it? The output here will allow DC to pass through. Small frequency signal it will allow to pass through, but at very high frequencies, the output will be zero, right?
Yes, sir.
Is that point clear? At DC, the capacitor acts as a open circuit. So whatever input you apply, output will appear same as that. Correct? But at very high frequencies, the capacitor, what does this do? Capacitor acts as a short circuit, isn't it?
Yes.
So whatever, so it will actually short to ground. So your V out will actually be zero at very high frequencies. So it is a low pass filter, right? It allows smaller frequency signal to pass through unhindered, but at very high frequencies the signal is actually not passing. Output is actually becoming zero, right? So it is a low pass filter, classic. Now there is something called as a high pass filter. Okay, high pass filter. What is a high pass filter? Tell me, how will it look like? High pass filter response. How should it look like?
Uh, it should be zero at low frequencies, and then
And
at
then
some
it should
frequency it should be.
something like this, right?
Yes.
There will be
But
a roll off to right. I mean,
yeah, correct. So that is what I'm coming to next. So in actual cases, you will not see like this. You will get something of this kind. Okay, okay.
Yes.
So tell me how will the, can you tell me how will the transfer function of this look like? H of S. You clearly see that here it is rising, right? So there should be a zero, right? At this point, you should have a zero. That is why it will rise, right?
yes, sir.
The magnitude is actually going up, which means that there should be a zero here. So let's say this is omega z, and here the magnitude is actually, it was going up, but suddenly it stopped going up, which means that here
There
what
will be
should
a
have
pole.
happened? There should be a pole, right?
Yes, sir.
Everyone following me?
Yes, sir.
Okay, good. So how should the transfer function look like? And let's say this point is the gain is actually k. So what will it look like? K upon k into,
1 plus
K
S
into
by
1
what?
plus
Z.
What
omega,
proportional?
1 plus S by omega Z
Z.
upon 1 plus S plus omega P.
S by. Yes, sir.
right? This is how it will look like, right? And yeah, this is how it will look like. So no, this does not look
I
right. This does not look correct.
uh,
What is wrong? Tell me.
uh, are these the Bode plots that the
Hmm.
magnitude in the Bode plot?
Come again.
So these are the magnitude that we are saying. These are in Bode plot, right?
Yeah, this is Bode plot, correct.
Yeah.
So, but I am saying what will be the S and Laplace transfer function? Does this look correct to you?
Is this because of the phase lead?
No, no. I'm asking, is this transfer function correct for this particular plot?
I think, yeah, I mean, in this case, the if the phase is there, then omega p is greater than omega z. Um, so it's gonna be an advanced system because 1 by or omega by omega z will be more than omega by omega p.
No, no. I'm not saying that. I'm saying, does this look correct to you?
No, sir.
So what is wrong? I mean, how can you easily say that it is incorrect?
Because the gain you have mentioned is at omega p, not at omega 0 to omega z. Like,
Yeah, correct. So you see that at DC or at zero frequency, when it is zero, the magnitude should have been zero, right?
Yes.
But it is not appearing to be when you put, so h of j omega, if you write here, k into 1 plus j omega by omega z divided by 1 plus j omega by omega p. So at omega is equal to 0, what will happen to h of j omega? It will be k, right?
Okay. Yes.
This is wrong, isn't it?
Yes.
Clearly wrong. So how do you fix it?
There will be a zero as well.
So this plot is actually not correct.
SS.
This plot is wrong. Okay, this plot is wrong. At till omega is equal to omega z, you do not have any this thing, right? So it will be like this. Something of this kind, right? Uh, Sorry.
I guess the one in the numerator won't come. Is it?
Yeah, 1 second. So that is not true because at yeah, so correct. Sorry, yeah, exactly. So it will be k into 1 is removed, so j omega minus omega z, okay, divided by omega z divided by 1 plus s over omega, 1 plus j omega divided by omega p. This is how it will look like. Okay.
How do you get the numerator there?
So this is also not correct actually because the gain k is at in very high frequency. Okay, so let's not complicate it. It's actually
Can it be S by omega z?
yeah, 1 second. Let's not. Yeah, I'm coming to that only, so that will be easier to see. Let's make it easy. So let's take a high pass transfer function of this kind. Mm, hmm. Okay, let's take a high pass transfer function of this kind. So omega z is actually at
so
0.
put k is equal to 1, then it will be correct.
Yeah, yeah, I'll do that. I'll come to k later. Let's say it is k only, but I'll come to k later. First of all, let me ask you this. So how will this look like? the numerator should have omega by, so this will not be 0, right? Omega, this is omega z is here. What is 0? The 0 is located at 0 only. So it will be s, simply s, right?
Yes,
S
yes.
divided by 1 plus s by omega p, something of this kind, right?
Yes, sir.
Exactly, right?
Yes.
So please mind
Yes.
it that this is not a magnitude transfer function. I mean, this is in dB, okay? So this is in dB. Please mention this is in dB dB of magnitude. Okay, and this is your omega. So this is how it is. So this is how it will look. Now at very high frequency, how will the transfer function look like? So h of j omega, it is j omega divided by 1 plus j omega by omega p. So at very high frequencies, at omega much greater than omega p, how will it look like? H of j omega divided by is equal to j omega divided by, so you can ignore this one, right? Isn't it?
Yes.
You can ignore this one at that point. So this will actually cancel and omega will also cancel. So h of j omega will actually become omega p. So it becomes a constant, right? At very high frequency, it becomes a constant which is equal to omega p. So this k should actually be equal to what? Omega p, right?
Yes, sir.
At very high frequency, it becomes a constant value, isn't it? So this is a high pass filter. Okay, so I actually got lost. Anyway, so this is actually a high pass transfer function, correct? Yeah, Ravi, ask what you have to ask.
Uh, yes. Can you please explain the logic behind like taking just S when we have either pole or zero at the origin?
Okay, so if why did I do that? Zero at origin means what?
Uh,
Plus 20 dB increase in.
So how will you write any transfer function h of s? You know that it is 1 plus, or not 1, it is s plus omega z 1 into s plus omega z 2, right? And so on, s plus omega z n, right?
right. Okay.
And this
So
is s plus p1, or rather omega p1, s plus omega p2, and so on, s plus omega p n, right? So
yes.
what is the zero location here? Minus omega z1, minus omega z2, these are the zeros, right? So if
Yes.
your, let's say it's only a one single, it only has one zero and only has one pole, and in that, say, let's say I am saying that the 0 omega z1 is at 0, which means what? How will the transfer function look like?
S by S plus omega.
Is that correct?
Got it. Yeah.
Yeah.
Yes. Yes. So
Okay.
we always look at for the zeros. I mean, for the standard in analog
Yeah,
electronics,
correct.
which is 1 plus S plus something. So if they are non-zero, we can look at that. For zero, we'll have to always
Yeah,
refer
because
to
this will also be reduced in that exactly like that. So if you take omega z1 out and here omega p1 out, then how will this look? 1 plus s
1
by
plus omega
omega
z1
z1 divided by 1 plus s by omega p1, right?
omega z2. Yes.
But you can only do this business when omega z is not equal to 0, right?
Yes. Right.
Otherwise, you cannot do this. You cannot take it out as common. So that is why you stick to this.
Sure. Got it. Thank you.
All right. Welcome. So this is understood, right? So that it means that in any high pass filter that we will see, we can expect a 0, right?
Yes.
Yeah. So which high pass transfer function? So what is the practical implementation of high pass filter that you know? Anyone? Any practical high pass filter? Like this this guy here, RC circuit. it acts as a low pass filter, right? So can you tell me any circuit which acts as a high pass filter?
We can interchange the capacitor and resistance maybe.
Yes, very good. So our friend here is saying that let's interchange the capacitor and resistor. So this is R, this is V out, this is C, this is V in, right? So tell me what will be V out by V in with respect to S, of course. It will be
R by R plus J omega C.
R by R plus 1 over SC, right?
Mm,
Yes. So what will it look like? So it will be SRC
SCR by SRC by 1 plus SRC.
1 plus
so C by
SRC,
SRC plus.
right? So as I was saying earlier, you see that in this system, this is a practical system, isn't it? This is a very practical system. No doubts there. This can be realized, right? On a
Yeah.
circuit. So you can clearly see that this system gives a zero, but it always comes with a pole, isn't it?
Yes, sir.
So this is
Yes.
actual this you will see is actually the case always. Whenever you try to create a zero, you will always have a pole. Okay, fine. So tell me, so this is a zero, right? Zero is at which location zero is at,
Again
right?
0.
And what is the pole location?
1 by RC.
Sorry. Yeah, 1 by RC, right? I think I made a mistake somewhere. Yeah, this is not correct. Omega p is equal to 1 by RC, not minus 1 by RC. Okay, so so what does this mean? What does this mean? Tell me. So how will the system behave? So if you give a unit step here,
So
how will the system react to that output?
it
How will
will
it look like?
start ramping up. It will start ramping up from the origin, but at omega p is equals to 1 by RC, it will like get to get to 1 value 1.
I mean, it will, yeah, it will look something of this kind. It will start, suddenly it will jump here, right? It will not do that omega p is equal to 1 by RC. It will jump suddenly, okay, at the output. It will suddenly jump and then it will start going down this way, isn't it? At the output, isn't it? So voltage across this capacitor cannot change instantaneously, right?
Yes.
What was the initial voltage across this capacitor?
0.
It was zero, right? Initially, isn't it?
Yes, sir.
Yes.
And when you
Yes.
suddenly increase the voltage from, let's say, 0 to 1 volt, what the voltage across this capacitor cannot change, right? But at this terminal, if the voltage has become 1 volt, what should happen to the voltage at this terminal?
1 volt.
Uh,
It should also
uh,
jump to 1 volt, right? Because
Yes.
the voltage across this capacitor was what? It is zero, isn't it? So across this terminal, the voltage, so let's say this is VA and let's say this is VB. So VA minus VB was initially zero, right? So even after the jump, just after the jump, immediately after the jump, it should still be VA minus VB should be equal to zero only, right?
yes, but for the cases when omega is very large, the capacitor acts as a short circuit, right? So all the voltage that we have at the input should be at V out.
So that's what
So
we have,
we
right?
cannot have, but V out, but V in is, but V
No,
in
no,
is
let me
one, right? V,
let me come to that. Okay, first let me ask you whether you understood this or not. That the voltage
yes,
at the across the capacitor cannot change instantaneously. Is that correct?
Yes, sir. Yes, sir.
yes,
Yes, good. So if the voltage across the capacitor cannot change instantaneously, mind it. Okay, I will come to this point, by the way, that voltage across the capacitor cannot change instantaneously. This is not a sacrosanct fact. It is not always true. I'll come to that later. But at this point, it looks like the voltage across the capacitor will not change instantaneously, right? And because of that, whatever initial the voltage across the capacitor was, just after this jump, just after this jump here, unit step, the voltage across the capacitor will still remain 0 volt, right?
Yes.
Yes, good. So if it is still 0, which means what? Here it is 1 volt, so this also should become
1 volt.
1 volt, right? So that is why it will first
Right.
jump. It will not look like this, but it will first jump like this here, and then after that it will slowly start deteriorating. And can you tell me why will it start going down?
Capacitor is charging.
It is capacitor is charging, right? Which means what? Capacitor will start saving the charge across it, right? And will start creating a voltage 1 volt across it, isn't it? And why is it that after a very long time I am saying that the voltage at the output will become 0?
Got it. So it's a DC basically after a very long time.
Ah, correct. So I actually made this point in the first session itself, right? That any unit step
Yes.
actually behaves like a DC after a very long time, correct?
Yes, sir.
Yes.
Yeah, and the capacitor is what? It will simply become an open circuit
Um,
for a DC signal, right? Which means that
yes.
no current can flow through it, which means that no current flow through resistor also, which means that the voltage drop across resistor is also 0, which means that V out has to become 0, correct?
Yes.
Yes, good.
So
Now,
can we say that when capacitor starts charging, then the speed of the charging of capacitor decreases, and then V out is decreased because the current is.
I didn't understand.
Sir, when the capacitor starts charging, then it builds up the voltage. Then the difference between V in and the voltage across capacitor is like decreasing, so the current is decreasing.
Yeah,
So
correct, exactly. That is exactly what happens. That is exactly what happens.
okay.
Yeah. Anyway, so now let me come to the point where the zero didn't manifest itself, isn't it? And can you tell me why did the not do anything here? It is because 0 is 0, right? The 0 is actually 0. So how will it do anything here?
Didn't get that.
Mm, okay, this will come to you when I do the next example. I'll do the next example. First, yeah, so let me just give another example here. Case number 2. So let's say this is case 2. And this you will understand very well if you understand this case 2. How will the transfer function look like here? So what is V out by V in here?
R parallel 1 by SC2.
Or let's say we make a small change. Let's leave the high pass filter. Let's take a low pass filter only. This is low pass filter, right?
Yes, sir.
Right.
But let's take this. Let's do this. Huh. Let's do this. So what will it? How will the transfer function look like?
1 by SC2 uh,
Mm-hmm.
upon
Divided
1
by
by SC2 plus 1 by SC2 plus R parallel or R parallel 1 by SC1.
correct.
Yes.
So what will be the final expression? Tell me. Hmm. Let me quickly do it. It will be R divided by 1 plus RSC1 or SRC1 SRC1 and so this will look like what? This will look like so 1 over rather 1 over so 1 plus SRC1 plus SRC2, right? And 1 plus SRC1. Is that correct? Is this correct?
Yes, yes, yes.
Yeah. So let me just write it fairly here. So V out upon V in, or rather, let's do it here. No, it's here is fine. So V out upon V in of S is actually equal to 1 plus SRC1 divided by 1 plus S into R C1 plus C2, right? Right?
Yes, sir. Yes, sir.
Hmm. So tell me something. What do you observe here? So what is the zero location now? Omega Z?
Uh, minus 1 by
No, no, it
RC
is not
or 1
minus,
by
please.
RC1.
Yeah, it is
1
1
by
by
RC1.
RC1. I didn't ask you what is SZ, okay? I
Yes,
am
yes,
asking
yes.
omega. So it is a real and positive number. Okay? And what
Right.
is omega P?
1 by RC1 plus C2.
Okay. Tell me among these two, which is larger? Omega Z, omega P.
1 by omega Z
Omega Z is
greater.
greater than omega P, right?
Yes,
Isn't it?
yes.
Correct. So tell me how will this system look like? The transfer function. If you plot h of j omega, so this is, let's say this is h of s. Now I want to plot h of j omega. How will this look like? So I'm also plotting, I'm also covering the Bode plot which I wanted to cover here. So how will this look like? Bode plot if I want to plot. So mod of h of j omega in dB. How will this look like?
Uh,
First, omega z is greater than
Uh,
omega p, right? So first I'll have omega p, then I'll have omega z, right?
yes,
Huh? Correct?
yes, yes.
So how will this look? At very low frequency, what is the gain?
okay.
What is the
Sorry.
gain? No, no, h of j
One, one.
omega.
It's 1, 1. It's 1.
So yeah, so h of j omega, let's also write it here so that you guys should not 1 plus j omega RC1 divided by 1 plus j omega R into C1 plus C2. Correct?
Yes,
Huh. So this will be at very low frequency, it is 1, right? So it will be 0
yes,
dB. So let's say 0 is here. Let's say 0 is here. Let's say 0 dB is here. Okay, and at the first omega p is it. So what will happen after omega p? It will start going down, isn't it?
cooling off. Yes,
It will start going down. Sorry. Oh, it'll start going down, right? And I'm just asking you, do you know what is the slope of this?
Uh,
20 dB, minus 20 dB.
minus 20 dB per decade.
Exactly. Very good. So the slope is minus 20 dB per decade, right? Correct.
Yes,
It is also written as minus 6 dB per octave. An octave means multiplication by 2. Okay,
Yes, sir.
twice the frequency. All right? Huh.
Yes, sir.
Good. So it is minus 20 dB per decade. But what happens after this omega z? Can you tell me here? What happens when omega becomes much greater than the omega z?
Gain will become constant after omega z.
Gain will become constant, right? What will be the gain?
Mm.
So at very high frequency, at omega much greater than omega z, the gain of the system will be h of j omega mod will be equal to how much? Omega r c1 divided by omega r c1 plus c2, right?
C1 by C1 plus C2.
C1 by c1 plus c2, right? So it will be
Mm.
something of this kind, and what will be this value? It will be
Ultimately C1 upon C1
c1 divided by c1 plus c2, but this
mod of
has to be in dB,
20
right?
log.
Yes,
So
Yeah,
sir.
20
20
log
log
of.
of this, right? So
Yes,
this
sir.
will definitely
Yes.
be a negative number, isn't it? Because C1 is less than C1 plus C2, right?
Yes.
Okay, good. So so this is how its transfer function will look like. Now tell me exactly what will happen when I apply a unit step here. One more thing, one last thing. Tell me whether the 0 is in right half plane or left half plane here.
Left half plane.
Left half
0 is
plane.
a left half plane 0, right? So what should happen?
Yes.
I should expect that the system is somehow getting faster, right?
Yes.
Correct?
Yeah.
Yeah, good. So if the system is faster, I should expect to see this in its unit step response also, right? So tell me, if this
Yes.
capacitor C1 was not present, how was the unit step response of this guy? It was
As it is.
like this, right?
Oh yes. Sorry,
Yes,
Japan.
sir. Yes, sir.
Yes.
Okay. So let me, I think I'll need bigger space. So let me plot it in a much bigger space here. Okay. It is t is equal to 0 here. So without this C1, so without C1, how was the transfer function, or how was the unit step response? It is something of this kind. So this is without C1, right?
Yes.
And now that I have used C1 here, can you tell me how will the transfer function, how will the unit step response look like?
So I mean that was definitely it's like reducing the delay,
No, no,
advancing
how?
it.
No,
So
no, let's say you do not know it is reducing the delay. I mean, you are a first
okay.
person. Let's say you are in standard 11 or 12. 12 is where you learn this for the first time, right? Electronics, right? Capacitors. So tell me from that perspective. So you do not know anything about this Bode plot and all. So, but
Okay.
you
So
just have to solve this. How will you solve it?
I think the
Uh,
voltage across the C1 will change instantaneously. Uh,
Why?
uh,
Why will it change instantaneously?
Sorry, at V out it will change instantaneously.
How?
I
How?
mean
How?
voltage
Why?
across because voltage across capacitor C1 isn't changing instantaneously. So that means whatever we have at V in, that will be reflected at V out
No. So see, yeah.
initially.
Uh, let
Initially,
me let
capacitor
me
C1 acts as short circuit, then the change in
And
V is directly
one
applied.
second, one second. Let me address this point here. Uh, Earlier I said that the voltage across a capacitor cannot change instantaneously, right? I said something like that.
yes,
But that happens. There is a reason for saying that, right? What is the reason? I cannot just make any blind statement, right? There has to be a physical justification of that. So you know that
the
voltage
charge.
across a capacitor is what? No, sorry.
Uh,
The current that is going to flow through a capacitor is given by what?
dV by
QC.
dt,
Yes,
C
yes, sir.
dV by dt.
Right? So it is what is VC? VC is the voltage across the capacitor, right? So let's say you have a capacitor here and the voltage across it is VC, then let me copy it and write it somewhere in below. So it's a small digression here. So let's say you have a capacitor here. Okay, the voltage across it is Vc. So what is the current that is going to flow through it? IC,
So that will be C dVc by dt.
right? Now tell me, if the voltage across the capacitor Vc changes instantaneously, what will be the derivative of this change?
Infinite.
It's infinite.
It will be infinite, right? At this point, if you take the derivative of a unit step, you know that the derivative of a unit step looks like a impulse, isn't it?
Yes, sir.
It looks like an impulse. And what is the height of an impulse? It is infinite, isn't it?
Hmm.
Correct? So, which means that if your unit step, if the voltage at the if the capacitor voltage across it changes instantaneously, the derivative of that will become infinite, isn't it? And if the derivative becomes infinite, which means that the current will become infinite, isn't it?
Yes, sir.
Yes.
Now tell me, if this capacitor is connected in this manner in a circuit. So now tell me, if the current through this capacitor becomes infinite, what do you think can go wrong here? Is that possible, by the way, in this case? Can the current become infinite here?
No, because
Why
there is
is
No.
why is that?
resistance.
Resistance, right?
We are. Yes.
If the
So
resistance
we
is
are.
if the current through the resistor becomes infinite, what will be the voltage across it?
Infinite.
That will also be
Infinite,
infinite.
right? This will become infinite, right? And you will see that the voltage across the capacitor is not infinite, isn't it? Because it's a finite step. The voltage across a capacitor is a finite unit step, right? It from 0 to 1 volt, let's say. It came from 0 to 1 volt, the voltage across the capacitor. However, the voltage across the resistor became infinite, right?
Yes.
And the voltage in this voltage source also is some finite value, which is 1 volt, right?
Hmm. Right.
Correct? It is also 1 volt.
Yes.
Now tell me, if the voltage across the this is 1 volt, this is also 1 volt, is it possible for this resistor to become infinite voltage?
No.
No.
KVL will be
Violated.
violated, right? Kirchhoff's voltage law will be violated. That is not possible, correct?
Yes, sir.
Which means that the only possible explanation is what? That the current through the resistor cannot become infinite, right?
Yes.
Which means that voltage across this capacitor cannot change instantaneously, right?
Yes.
Yes.
The voltage across the capacitor cannot change instantaneously means what? It will start gradually, right? The voltage will start gradually changing across the capacitor, isn't it?
Yes.
So that is the reason that we say that the voltage across the capacitor does not change instantaneously. It's because a resistor is present here, which will not allow that to happen. Now tell me something. If instead of this resistor, I have a capacitor here. Now tell me something. Now is it possible? Can the
Yes, sir.
voltage across this capacitor change instantaneously Vc?
Yes, sir.
Again, the same thing will happen, right? The voltage will change instantaneously. So there will be a instantaneously, there will be a infinite current will be there, right?
Yes.
Right? There will be infinite current. Now, what will happen due to that infinite current across this capacitor C?
Capacitor get charged and
It will
it
It
will
will
instantaneously get
charge
charged, right?
infinite.
But the voltage across it will be not infinite, right? It will be finite voltage. It will
yes
get
sir.
charged instantaneously, but the voltage across it will be finite, right? And why is that? Because the voltage across the capacitor is the integral of the current, right? Right?
Yes.
The voltage across this capacitor here is the integral of the current that is going to flow. So even if the current becomes very large for a very short duration of time, the overall integral will still be a finite number, right?
Yes,
Right.
sir.
Okay.
Correct? So that is why
Yes.
the voltage across this capacitor here in this manner can change instantaneously, right?
Okay.
Yes. Is that point understood by everyone? Yes, this is a very important point,
Yes.
by the way. This idea that what I'm trying to convey to here today, this will help you in analyzing circuit and even help you with your interviews a lot. This kind of analysis. Whenever you see something of this kind, capacitors in the loop, you can actually see that here a complete circuit path is actually completed by only capacitors, right? And the voltage source. So whenever you see something of this kind, you should expect that there will be a zero somewhere, and that is what I'm coming to next. So anyway, did you understand that in the presence of something of this kind, if there are only capacitors in the path, then there can be a sudden voltage change across capacitors, right?
Yes.
So now tell me something. Even if there is a resistor present here, will that matter change anyway? Will this change anyway the analysis that we did just now?
No, I think because the presence of capacitor, uh, I mean, wouldn't let it
Yes,
the
yes,
voltage
go on.
become to be infinite. Because it will charge, so it will take
Ah,
up. It won't
correct.
let all the.
So basically, okay, let me rephrase what you are trying to say, and let me just confirm whether this is what you were trying to say. That in the initially when this suddenly become when the input suddenly gave a step here, at that time the voltage across the capacitor, let's say it changed instantaneously, will actually make sure that this will actually induce a infinite amount of current, right? And that infinite amount of current, rather than flowing through this resistor, it will prefer this capacitor, right?
Yes.
Is that point understood by everyone?
Yes, sir.
Yes.
Yes, sir.
So initially at initially just at the time when the capacitor, then when the input voltage made a jump, at that time all the current that is flowing in the circuit will prefer flowing through capacitors only, right?
Yes, sir.
So all the current will try to flow through the capacitors only. It will not try to flow through this resistor, right?
Yes.
Yes.
Okay, good. So if that is the case, then uh, then it is now analyze the circuit. I'll tell you how. So come to this point here. Now tell me, if this suddenly goes from 0 to 1 volt, and let's say C1 is equal to C2. Okay, C1 is equal to C2. So tell me what should happen to the V out. I mean, how will the profile of this look like?
V in by 2.
Exactly. So V in by 2 what? V in by 2 exactly what? So how will it look like? I'm saying, I'm asking.
For, I mean, t equal to 0 plus, it will become V in by 2. But at t,
Exactly, exactly. Yes, good. So it will suddenly jump to V in by 2. Okay, here.
yes.
Suddenly, instantaneously. And then after that it will start doing this, isn't it? Is that point understood?
Yes, sir.
Right? So
Here, sir, I mean, how we calculate the steady state value without doing this type of, I mean, Bode plot, without doing Bode plot, how can we get the steady state value? We get the initial value, right? With this logic, when C1, C2 is in series, so current can flow through directly through the capacitor and it gets charged instantaneously.
yes,
But I want to know, without applying this Bode plot, how can I get the final value?
okay. So tell me, first of all, let's not jump there. First let me ask you whether you understood this or not, that
Yes,
it will
sir. Yes,
suddenly jump.
completely.
This is understood by everyone, right? This is a very important point. Please confirm whether you understood this or not. Only then I will move forward.
So I have a question. Like,
Yes.
will the time constant be the same in this
No, it will
case as
not be
well?
same. It will not be same. Definitely, you see that this omega p, the time constant will be dictated by pole, right? And you can see clearly that this there is extra capacitance which you have added here, right?
Yes.
There is C1 plus C2. It is not only C2, it is C1 plus C2. So time constant will change definitely. But what I'm trying to stress here is that you can see clearly that there is an initial jump, isn't it? And that jump is
Yes.
actually moving you, pushing you in the direction of where you wanted to reach in the final steady state, right?
Yes.
So this is like the system is pushing you in the direction, in the right direction, right? The system is pushing you in the right direction, which means that the system is actually advancing you in the right direction. Huh? So this is what a
Uh,
zero does. This is what a zero in the system does. It will always, if it is a left half plane zero, it will push you in the right direction. It will push the overall feedback in the right direction. Okay. If there is a left half plane zero, it will push the output in the right direction instantaneously. And that's how we say that a zero helps in reducing the delay. Got it?
In
Hmm.
this case, when the extra capacitor is present at like the
Huh.
C1,
Hmm.
so without that, so uh, I mean the without C1, whatever the output was,
Hmm.
that's advanced, right? Can
Yes.
we put it the other
Yes.
way?
Yes. That's what I'm
Okay.
saying. That's how it is. That's how it is actually. That is why it is advanced, right? You
Right.
can see
Okay.
clearly that initially you can see there is a boost, isn't it?
Mm,
This point, you can see that at this voltage you were reaching only after so much delay, right? But here you instantaneously
yes.
jump. This is how its system is. The zero, a left half plane zero helps in advancing the system. It advances, which means that a zero, whenever there is a zero, it will either advance it in the right direction or it will delay it further in the wrong direction. So it will always give a push initially. This is the final point that I want to make in this regard, in the regard of a zero, that whenever there is a zero, it will always affect only the initial condition. Okay, it will always affect the initial position of the system. If it is a left half plane zero, initially it will boost the system in the right direction. Okay, if it is a right half plane zero, it will initially push the system in the wrong direction. So had there been a right half plane zero in this case, what would have happened? It would have gone in this way, so that it would have done this initially, and then it would have started doing this. So this happens when there is a right half plane zero. Okay. So this happens when there is a left half plane 0. So whenever you are trying to add zeros, you have to make sure that the 0 is in the left half plane. Otherwise, there will be a catastrophe. So this is even more delayed, right? This red curve here.
Ye- Yes.
Yes.
What happened when we apply a pulse, like
What
pulse
pulse?
input? Pulse input.
You can do that
Yes.
analysis now. I mean, this is uh, this is a unit step, right? So you can do that analysis. What happens when you apply a pulse?
Okay.
But this is understood, right?
Yes.
Yeah, and now addressing that question which someone asked me, how can you find out what is the final value without looking at the Bode plot? So, what is meant by final value or the steady state value? It is
Sir. Can you consider the second circuit where R is connected to V out to ground? Yes, below.
oh this one.
Yes. Yes.
Okay, tell me what will happen. You tell me what should happen if you apply a unit step here. What should happen? Initially, it is understood that the unit step will actually do it something of this kind, right?
According to the capacitor value, it will get the jump. And at final value, we can think like that capacitor will get open circuited. I mean, is
Yes.
this intuition correct?
Yes, exactly.
Okay,
That
okay.
is how it will. and then it will suddenly become, and it will slowly, gradually
Okay.
go down to zero.
Okay. Okay.
Okay?
Got it. Got it.
Yeah.
Got it, sir.
Okay. Fine. So this is important. So this I wanted to, oh, actually I missed a lot of things which I wanted to explain and didn't touch anything else. And the time is already up. All right. So I apologize for that. I actually got carried away with this. But this is actually a very important point which I wanted you all to understand, because everything else you will get in the lectures. This is something which is often not covered by people. So this is important. This is actually, this intuition will actually help you in your interviews also. This will
Yes, sir.
come.
I got that question in my interview also.
Yeah, this is actually a very important point. Nyquist criteria, I'm sure you understood. I mean, this is nothing, there's no rocket science going on here. I mean, especially, I mean, you do not need to go into maths of it, so that is why there's nothing to comment about it. It's just that you understand, you just have to understand what is Nyquist criteria, that's all. You just have to apply it. This I wanted to explain to you, but all right, I couldn't get the time to explain, and that's fine. What I would advise you all guys to do is that you have the link to my channel, right?
Yes, sir.
Yes.
Please, you can, I mean, in my channel, I have uploaded. There's a the same course. This was done in 2024 also, right? Yeah, last year. Or yeah, last year I think. No, no, last year, 2023 I think. So I have uploaded this, the same kind of a lecture there also. There I have discussed all these things. So maybe you can go back and take a look at the other points. And also I have covered some questions there which will help you in solving the questions. So please try and go and look at that lecture, okay? So those who do not have the link, please don't worry. I mean, the links are there. Whatever link I have applied, there is a link that is shared to you, right? Every week, the YouTube lecture link, right? From on that
Problem solving session.
yeah, problem solving session, correct. In that you go and then you click on that link. You will be directed towards my channel.
Sir, I
Okay.
have
Yes. Go ahead.
two doubt.
Yes. Go ahead.
I mean, it's on based on the assignment three statement. So the statement said that
Yes. Tell me.
the statement said that an op amp has a DC gain of 10,000 V by V voltage by it should be voltage by second, right?
No. How? Why?
V by V. I mean,
What is meant by gain?
gain means V naught by Vi.
Huh. Both are V naught, right? Both are V out is also in terms of voltage. V in is also in terms of voltage. So that is why it is V by V
Okay.
dimension. It is a dimensionless quantity, isn't it? The gain does not have any dimension, does not have any unit, isn't
Okay.
it? Yeah.
And this gain, I mean, here this circuit is can I consider this is a closed loop circuit? I mean, the gain
Okay,
of this.
I'll tell you how it will look like. Unity gain feedback is this. This is a unity gain feedback.
Hmm. Okay.
This is unity gain feedback. I wanted to discuss this question, but I couldn't get the time. It's okay. You try to solve this on your own after looking at the lecture which I uploaded last year also. Okay.
Okay.
So yeah. So anyway, yeah. Again, let me re-announce what I did at the class earlier at the start of the class. I'll not be present for the next 2 weeks. I'll not be here. I'm traveling outside, so the sessions on 17th and 24th I will not be able to hold. However, the lectures, I mean the sessions on 17th and 24th will be on week 4 and 5, right? And for both of them, the videos are already uploaded in the last year sessions, so you can take a look at them. If you have any doubt, we can cover them later. Okay. At this point of time, I am not planning on taking any makeup classes for that. Is that okay? If you have any
Okay.
doubt, I will. You can ask me if there is a requirement. I will take an extra class. Otherwise, I will not do it. Okay?
Can you drop your mail, sir, so we can contact through mail? I mean, any questions only.
You can post on the forum. I will be looking at that. Okay?
Okay, sir.
Huh. Try to go through the lectures that are there in the that discussion sessions which you uploaded for last years. So you will be able to, I think you will be able to do all the assignments and you will be able to understand. Okay? 17th and 24th, I will not be able to hold the sessions. Okay, thank you. So I think that would be it. Let's meet again after 2 weeks. Okay? Thank you all. Thank you all for joining.
Thank you, sir. Good night.
Thank you.
Thank you. Thank you,
Thank
sir.
you.